and the metals are all the elements which is here. So it means that around this line, you have the metal here, except hydrogen, which should be here, okay? So in this part, you have all the organic compound elements, and the metal indeed has the definition of a metal. It's an element who has electronegativity, a low electronegativity. Okay, so metal are used by humans and other life form, you know that. And in this periodic table, you can have the micronutrient in pink. So the micronutrient here in pink are the nutrient, the micromineral that are required in large quantity. And you have in green the micronutrient, and the micronutrient are required by human and other living things in small quantity. Okay, usually for people, we need only 100 milligrams per day. And the micro elements, it's required. So you have in this table the biological function of some trace elements, so some metals. So you have iron, copper, manganese, zinc. We will see some example of proteins which need these elements. Cobalt, which is the component of a vitamin, B12, and the other. Okay. The first problem with the metal is that we use the micronutrient in much higher concentration. We need this concentration that they are available in the environment. So you see in this table the concentration of the micronutrient in the seawater and the concentration in the blood. Okay, so it means that we have to concentrate, require these metals and concentrate them to be used in the body. The second problem with metal is their toxicity. Okay, so many metals are toxic in living things, including those that we also need. So we have here quality of health against the dose of metal. So when you have non-essential metal like mercury, cadmium, you know, in Vietnam, one of the non-essential metals, the toxic metal will be arsenic. We can find a lot of quantity of arsenic in Vietnamese water. And we have also this curve for essential metal. For this, we have, let's see, 5 parts of this curve. At the beginning, it means when you don't have enough of these metals in the body, because they are essential, it means that if the concentration is too low, you will have death. Okay. After that, let's take another color. U, it's the concentration, or it will be deficient. When you reach the plateau in this, so it's it's the required concentration of metals in the body. So this is the optimum concentration of this metal in the body. If the concentration is too high, you will have a toxic concentration of these metals. And at the end, you will have death also when the concentration is too high. Okay. You have the metal toxicity. It's also a factor in a lot of disease. So I'll give you some example. So for the Wilson disease, it's an accumulation of copper. Do you have any question? No? And in the case of iron accumulation, if you have two iron, it's called hemochromatosis. Okay, so this is two disease involved in the metals accumulation. And also the toxicity of metal, it's because they can reduce oxygen and create free radical. So because they can reduce O2 to superoxide or hydrogen peroxide. So this compound, you know, it's the Ross species, reactive oxygen species, and this compound, this molecule are responsible to the oxidation stress. Okay? Oxidation stress. So this species will react with proteins, DNA, and you know it will cause damage. So you see that we need a balance for the concentration of the metal to get them from the environment, but to store them in the body in a non-toxic form. So, for example, in the iron metabolism, you have a lot of proteins involved in the iron metabolism to absorb the iron, because the iron absorbed from diets or from recycle from erythrocyte. Okay, this iron will cross the cell by several transporters, store in protein which is called ferritin. You have two oxidation states for the iron 2 and iron 3. I already told you that iron 2 and iron 3. Iron 3 is insoluble in biological media. That's why we need a protein to transport the iron, and this protein is transferrin. This transferrin allows the transport of iron by the receptor endocytosis. Okay, and you have also proteins, because the iron absorbed it's in the oxidation state of 2. The transferring will be loaded by iron in the oxidation 3. So we need some protein, some enzyme, the oxidase, which are able to oxidize the iron 2 on iron 3 into iron 3. So we have two proteins, ephastine and also the ceruloplasmin. So all these proteins are involved in iron metabolism to take the iron from the environment, to allow the transport of iron into the cell, because you know when you have anion, it's very difficult to cross the membrane, the membrane. So that's why we need some enzyme and proteins. We have enzyme also to store the ferritin and release the iron when it's needed. So the role of metals in the body, we have three roles. The first one is because they are Lewis acid. I will explain you that. Because they can have oxidation and reduction chemistry, we can adopt the metals, can adopt more than one stable redox state. And also because they can make coordination chemistry. So let's see. So for the Lewis acid walls, you know that the water have a pKa of 14. When the water is coordinated to a metal like zinc, what happens? The pKa decrease, so the water can form rapidly, more easily, this species O minus with a pKa of 10, and it's very important because why? Because this species is a nucleophile and he can react in an enzyme. And in a protein like carbonic anhydride, you have a pKa of 7. It means that at physiological media, you have half of the water like H2O and half of the species like HO minus. Let's see in this slide. So this is the okay. So this is the carbonic anhydrase. So you have the protein, the active side with a zinc here, and the zinc is coordinate with 3-histidine. Okay, and we will see that it will activate water to make potent nucleophiles. So this is the same active site. You have the zinc coordinate with 3-histidine, and the fourth ligand is the water. The first step is the release of a proton to have the OH minus, and this is this reaction with a pKa around 7. So it's very easy to do this reaction because of the zinc and because of the protein environment. In water, you have this reaction with the pKa of 14. Okay. After that, the CO2 can enter into the active site. And then because you have the formation of HO minus, you create a proton nucleophile, which can react to the CO2. Oh, sorry. And then after that, you have the release of the HCO3 minus, and the water will take the place of your substrate, and you can make a cycle. So the presence of the metal and the presence of the protein reduce the pKa value of the water, of the couple water HO minus, okay? For the oxidation reduction chemistry, sorry. So because of the metals coordinate with several ligands, you will have a large variety of redox potential. And we will see it's very important to have a large variety of redox potential. So I will give you an example here, but at the end of my lecture, I will give you other examples. So you have ubedoxine, ferrodoxine, and so on. And finally, the last role, it's the structural role of metal. So indeed, why we use metal? Because they can do other things than carbon. So metal have the ability to exceed the octet. So it means that it can be coordinated by more than 4 groups. In the case of carbon, you have only 4 groups attached to the carbon. In this case, with metal, you can have 6 or more than 6 groups attached to the metals. Metal will give you flexibility and ability of the structure. So for example, we will see the myoglobin, and in this case, the iron, it's the oxygen can bind and be released from the iron. And the last role is the scaffolding of protein folding. We will see in an example, but the zinc alone in some proteins, the folding of the proteins. Which ligands for which metals? So there is a theory which is called hard-soft base, acid-base theory. So it's the same theory that the Pearson acid-base concept. In this theory, we classified the metals and the ligand are soft and hard, okay, and the medium. So the hard acid, for example, the metals, the cation, hard acid, are small atomic ionic bodies. The metals are in the high oxidation state. Because they are small, they are low polarizability. And for the base, so the ligands, it's high electronegativity. For the soft, so you have this kind of metals. This is the contrary. So you have metals with large atomic or ionic wedges, a low oxidation state, high polarizability, and for the base, a low electronegativity. And the Pearson concept tell, like in French I said, qui se ressemble s'assemble. It means the hard acid will interact more easily with the hard base. So you will have hard interaction, and the soft acid will interact more easily with have more affinity with soft base. So you will have soft interaction. Okay. So in biology, the ligand will be amino acid, DNA, usually the phosphate group, sugar with the hydroxylate group, and we will see the cofactor prosthetic group, and in ferritin, it will form aggregate. So in proteins, so we will have amino acid, which can interact with the metals. So usually it will be the side change of the amino acid. So it will be heteroatom, which can react with the metals. So you have the OH group of serine, the sulfur of the methionine, the thiol group of the cysteine, OH of the threonine, la serine. One of the most common ligand it will be histidine with the 2 nitrogen, tyrosine also with the OH, and histidine we already saw that, but we know that we can have histag protein, so protein with several histidine at the end or at the beginning of their sequences, and it allows the purification of this protein because histidine will react with nickel, and this is, you have to see that with the affinity chromatography. If you remind that. We have also the carboxylate group of glutamate and aspartate. Don't forget that you have also the oxygen and nitrogen of the polypeptide chain. So some example of metalloprotein. Here you have plastocyanine. So it's a copper containing protein involved in electron transfer. Indeed, the metal can be copper 2 and copper 1. You can have oxidoreduction in this case. And you see, so it's a protein which is monomeric with a molecular weight of 10,500 Dalton with 99 amino acids. And we can find this enzyme in plants. And so you have the active site here. So the copper is linked to a cysteine, the thiol group of the cysteine, the sulfur group of the methionine, and to histidine. Now, a more complicated metalloproteins, it's an enzyme. So it's a methane monooxygenase. So this enzyme can oxidize. I'm sorry. Methane onto methanol. And we can find this enzyme in bacteria which are called methanotrophic. Okay. The active side of the methane monooxygenase has two iron in the oxidation state 3. So the iron are linked with an histidine, 2 glutamate, or 1 aspartate, which is monobidentate. It means that the 2 oxygen of the aspartate of the carboxylate group are linked to the iron. You have a glutamate, which is bridged between the 2 iron, because the carboxylate group of the glutamate, 1 oxygen, it's linked to the first iron, the second oxygen to the second iron. And you have also a water molecule, which form a bridge between the 2 iron. And you have 2 water molecule at the 6 ligand. So do you know why this enzyme can be important? The methane. What is the characteristic of a methane in the environment? The methane as CO2 is a greenhouse gas. You know what is it? Hello, is there somebody? So nobody knows what is a greenhouse gas?
Greenhouse, is that CO2?
Yes, but methane is also a greenhouse gas. It means it's involved in which phenomena, which is very important for us viewers.
I read about methane being a greenhouse gas. So,
I heard about before, but I don't know. Indeed, it's in the gas, the greenhouse gas, like methane or CO2. It's involved in the global warming. That's why it's important to reduce the concentration of methane in the atmosphere, because you will increase the temperature of the Earth. Okay, that's why we try to reduce the CO2. We try to reduce the concentration also of the methane. Okay, and a way is to use the bacteria, which has this kind of enzyme, to reduce the methane to methanol. Okay, so it's very important to the environment and to the Earth. Okay. Last protein structure, it's the zinc finger proteins. So it's a DNA bending protein, and there is zinc linked coordinate to 2 histidine here and 2 cysteine here. Okay. So we have here decrease CD, circular decrease spectra of the proteins in the presence of zinc. So you have the dot line. So if you compare with this, what is the main secondary structure of this zinc protein, zinc finger proteins? We have two minimums around 200 nanometer. It means that it's what is this?
File structure.
Sorry, I didn't hear you.
The alpha.
Yes, alpha-helix structure. If you compare this, and when we remove the zinc with a ligand, which is called a DTA, that means that the protein is without the zinc. We have the black lane, and it's typically a random call, something unstructured. So in this case, the role of the zinc is to fold the proteins into its tertiary structure. Without the zinc, you have a denatured protein because on the CD you have a random call. Okay? So you have, if you see the structure, you have an alpha helix, you have a string with a beta sheet with two strings. So we can see the string to form the beta sheet and the alpha helix here. In the alpha helix, you have two histidine separated by 3 amino acids. But if you remember, we see the top view on an alpha helix. If I have the -1 amino acid, the second one will be at 100 degrees from the first one, the third one 100 degrees. Remember that for each amino acid you have 100 degrees, and because of that you will have the two histidine on the same side of the alpha helix, even if are separated in the sequence by 3 amino acids. And because these two histidine are in the same side of the alpha helix, it can be coordinate. They can be coordinate to the metals, and so the zinc will fold the protein. Okay. Okay, so we see some proteins with metal which are coordinate with amino acid. Let's see another group. So this is the prosthetic group, so also called cofactor. So you know we also already saw that, but a cofactor is a non-protein chemical compound that it's bound to a protein and that is required for its biological activity. Okay, we define two types of cofactor that can be organic or inorganic, and we can separate them in two groups: the coenzyme, which is loosely bound to the proteins, and the prosthetic group, which is tightly bound to the proteins. Okay, so in our case, I will show you some example of prosthetic groups. So there are organic molecules, which is different of proteins. They are tightly bound to the enzyme, the proteins. Okay? So the porphyrin, this is the common structure of porphyrin as this. They are heterocyclic microcycle composed with 4 with ring, which is called pyrrole, but you don't have to remind that. And they are aromatic. Okay? So you will have, depending on the substituent of the porphyrin, several names. So you have in A, in B, in C. And in the center of the microcycle, you have 4 nitrogen and the metals. You can have a metal which will be coordinate with this 4 nitrogen. So the porphyrin metals are usually iron, copper, or manganese. Okay? So you see the substituent of the porphyrin. Tell me what kind of interaction you can have between the porphyrin and the proteins.
We may have ionic interaction.
Yes, perfect, because you have carboxylate group. You can have ionic interaction with these groups. With this tail, which probably hydrophobic or hydrophilic, this kind of tail. This one.
Hydrophobic interaction.
Yes, sure. This, you have a long carbon chain, so probably maybe with this you can have the ends at the surface of a membrane, or you can have hydrophobic interaction with the membrane. Okay, and in the case of MC, for example, you have already the interaction between the thiol and the cysteine, so it's covalently bound to the proteins. Okay, you have other example with the molybdenum, cofactor with molybdenum, chlorophyll here. So the chlorophyll, it's involved in the photosynthesis in plants. And you have the vitamin B12, sorry, vitamin B12. So here, this is just only example where a metals can be linked to a carbon. In fact, the X here is CH3. This is the only example in the body where the metal is linked to a carbon. Otherwise, always the metal are coordinate with heteroatom. Okay? So, I will explain you 2 proteins, the myoglobin and after the hemoglobin. So we will see that proteins, one of the function of proteins is the binding of other molecules. In our case, it will be oxygen. So the other molecules which binds to the protein are called ligands. We will see that the binding site is complementary to the ligand in terms of shape, charge, or other chemical properties. And then the interaction of the ligands to the protein are usually specific. We will see that the protein structure are not rigid. You can have change in the conformation, okay? And it will be very important for being. The binding of a protein to a ligand, it's often so coupled with a conformation change. It's called the induced fit. It means that when you bound the ligands to the proteins, you will have a change in the conformation to increase the affinity of the ligands to the proteins. Okay, and in the case of hemoglobin, we will see that the subunits of the subunit proteins can have a conformation change just after the bending of ligands, and it will affect the conformation of the other subunits. Okay, so we will see all these properties of proteins with hemoglobin, and first we will start with myoglobin. So myoglobin, you know, these proteins is a monomer of 17 kilodaltons with 153 amino acids. This protein has 8 alpha helix, which is called A, B, C, and so on. So we will see probably so H from A to H. We will see in some old article, you will see that the sequence depends on the helix. We find these proteins in vertebrate, and the function of this protein is to store the oxygen. Okay, so you have the structure of the myoglobin here. You have the 8 alpha helix, and you have a prosthetic group, which is an IMB. Okay, in the center of the IMB, you have iron. Okay, so iron is coordinate with 4 nitrogen. Iron can be coordinate, and it can have until 6 ligands. You will have an histidine as a 5th ligand, and so on the top of the IM you have something empty, so you can bind the oxygen. Okay. So the IM, I told you that because it's a prosthetic group, it is tightly bound to the proteins, and indeed in the myoglobin, the IM is bound in a deep pocket, and you have the amino acid on the pocket in red. So you have phenylalanine, valine, leucine, valine, leucine. What is the characteristic of all the amino acid in red? Is it hydrophobic or hydrophilic?
Hydrophobic.
Hydrophobic. Indeed, you have a lot of carbon and hydrogen. So the IM is rather hydrophobic, so it's not soluble in water. So we need a hydrophobic pocket to interact with the IM. So that's why you have all this amino acid. Anyway, you have also, like we already said, that we have carboxylate group, so we can have an ionic interaction with this carboxylate group, and for example, like which is positively charged. Okay, so at the distal part of the IM, so on the top of the bottom of the IM, you have an histidine, which is coordinate to the iron. Okay, so this is the bottom and the top. So here you will have the oxygen. So the oxygen-free myoglobin, it's called deoxy. Okay, the oxygen loaded protein the oxygen loaded protein, it's called oxy. Okay, so when you have oxygen, it's oxy. Without oxygen, it's called deoxy. In the deoxy form, you have iron 2, sorry. The iron, it's in oxidation state 2. It's pentacoordinate, and he has an iron radius of 78 picometer. Picometer, you know what is it? It's 10 minus 12 meter. Okay? And this radius is too large for the porphyrin. So the iron, it's below the plane of the porphyrin. Okay? So you can see in this, you have a side view of the porphyrin. The porphyrin is usually plane. And we can see that the iron is 0.4 angstrom below the plane of the porphyrin. You will see it's very important. In the oxy form, so when you have the oxygen, it's still iron 2. And this time, the diameter, the radius of iron 2, it's 31 picometer. 61 picometer. And now this metals, this radius is well adapted to the porphyrin. So the iron is in the same plane than the porphyrin. Okay, we can see that. So in the deoxy, it's out of the plane. In the oxy form, it is in the plane. Why we need a protein? Why we cannot use only a porphyrin to transport the oxygen, to store the oxygen? The first reason I already told you, it's because the heme is not soluble in water. Okay, so it's not soluble in biological media. So we need something to have something soluble in the biological media. That's why we have a amino acid, a peptide around the porphyrin. Okay, and also when the porphyrin binds the oxygen will lead to the oxidation of the complex and conduct to irreversible dimerization. Okay, you have this equation. So you have here the porphyrin when it's react with the oxygen. So oxygen binds to the iron. And you have the oxidation of the oxyporphyrin with the desoxyporphyrin. And you have a dimerization of this DM. Okay? So when you have a denaturate myoglobin, it means that you have the peptide change. This dimerization, the rate of this dimerization decrease. Okay? But if you have a fold hemoglobin, you will avoid this dimerization. Okay? So you have two reasons why we need a protein, a peptide to the M, to surround the M. We need, why? Because the M, it's insoluble, and he can form dimer. The proteins will soluble the M in the biological media and avoid the dimerization of the M. This is the absorption spectra of hemoglobin. So we have a change in the wavelength for the desoxy and oxy form, and the maximum of absorption is around 120 nanometer. That's why the blood are red. Okay. So we will see so for the myoglobin, because it's not an enzyme, we will also anyway can measure the saturation of the affinity of oxygen to the myoglobin. Okay, so we have this equation: myoglobin plus O2 will give MbO2. So the dissociation constant, which is the reverse of the affinity constant of O2 for the myoglobin, it will be concentration of myoglobin. O2 is a gas, so it will be pressure of PaO2 and the concentration of the oxyform. Okay. We measure the saturation Y. The Y, O2, is the fraction of ligand binding site on the protein that are occupied by the ligand. It means that it will be the concentration of the oxy myoglobin over the total concentration of myoglobin, so the desoxy and oxy. Okay, this is the fraction of protein which are in the oxy form. Okay. With these two equations, all right, I will go there. We can express the Y with a KD value and the concentration, the pressure of O2. The Y O2, it will be PO2 over PO2 plus KD. We can P50. So the P50 is the pressure of O2 the P50 is the pressure of O2, where the myoglobin is half in the oxy form and the other half will be in the oxidation desoxy form. Okay, so the saturation curve of myoglobin against the pressure of oxygen, it's like this curve. It's a hyperbolic curve. Okay, and the P50 of the myoglobin, so it's here. It's for this proteins 3 to 5 torr. Okay, you have the units here. 1 torr is 1 millimeter of mercury, or it's 0.13 kilopascal. Okay, so indeed, the oxygen binding to myoglobin, it's more complicated than a simple equation. So I will give you the mechanism and we will discuss about that after. So it's the bending, as I told you, it's influenced by the protein structure. So in the first case, you have the myoglobin with iron, which is pentacoordinate. So this is the deoxymyoglobin. On the active side, you have the valine, the histidine, which has a hydrogen bond with the water and a leucine. Okay? So the first step is the release of the water. So now the active site is empty and the oxygen can go inside. Okay? After that the oxygen enters in the active site, you will have the coordinate bond between the iron 2 and the oxygen. Okay? And you have a stabilization of this form because of the histidine here. You can form hydrogen bond between the hydrogen of the histidine and the two oxygen of the oxygen. Sorry. And this stabilization is very important. This is why the CO, the carbonyl, can bind less easily than oxygen, not less easily. Indeed, I will. The CO binds 20,000 times better than O2 to free iron, so free heme, sorry. Okay, that means that the heme has a higher affinity to CO than to O2. But only 200 times better when the heme is bound to hemoglobin. When heme is bound to hemoglobin. Myoglobin, sorry, not myoglobin. And why? This is because of this, the last step, the stabilization step. In the case of O2, this constant is around 1000, and in the case of CO, it's only 2 or 3, because indeed you have a lot steric entrance, because in the case of O2 binds to the oxygen, you have an angle of, let's say, 120 degrees. But in the case of CO, you have an angle around 180 degrees, and you have steric entrance here with the histidine. And here you have stabilization because of the H bond. You know that we can be unpoised with the CO. What? You know why now? It's because the CO can bind the hemoglobin, myoglobin, and take the place of the O2. Do you have any question here? No? Let's go with hemoglobin this time. So hemoglobin, what time is it? Okay. Hemoglobin is the tetrameric proteins. It contains 4 heme, one on each of its 4 polypeptide chains. So you have a quaternary structure with its hetero tetramer, heterotetramer with 2 alpha chain and 2 beta chain. Okay. Each of these chains has 156 amino acids. So you have a molecular mass of 64 kilodalton. It's the same origin. It's from vertebrate, and the function now it's oxygen transport. Okay, so the hemoglobin, because it possesses 4 heme, it can bind 4 oxygen molecules. So let's compare the protein structure of myoglobin and one of the subunits, the subunit beta of hemoglobin. Okay, you can see it's very similar. You have the 8 alpha helix. You have the heme with the iron. So the 3-dimensional structure of the 2 types of subunit are very similar. And only if we compare the amino acid sequence, you have only 40% of similarity in the sequence. Only 40%, but you have the same structure. Okay. So why we need hemoglobin? So if we see the saturation curve of myoglobin, you can see in green. Okay, in green it's a myoglobin. The pressure, oxygen pressure of the lungs, it's 100, around 100. Okay? In the tissue, it's 20, the pressure of oxygen. It means that if we use only myoglobin, so you will release only 7% of oxygen. Okay, so this is in case of we have only myoglobin. Okay, with a hyperbolic bending curve. If we have also another proteins, which is non-cooperative, we can have the release of only 38%. And why we have hemoglobin? If you observe the saturation curve of hemoglobin, is not now a hyperbolic, but it has a S shape, like an S, yes. And this time we have, the curve in the lunge has 100% will be saturated, and he will release now 66% of O2. Okay? So we have indeed this proteins which has something particular, which is called the cooperativity. So what is it? So we call also allosteric bending of O2. So you have hemoglobin, which can bind a number of oxygen. Normally it would be 4 because it has 4 heme. Okay, we can define a dissociation constant of this equation. We can define the Y, the saturation of O2. So this is the same definition. It's the fraction of protein which has an oxygen as a ligand. So this is the ratio between the oxy form of the hemoglobin and the total concentration of hemoglobin. Okay, and we have, if we combine these two equations, you will say that we have PO2N over PO2N plus Kg, which is the P40. Okay, and so we can plot what we call, this is the Hill equation, so we can plot the Hill plot. So this is the logarithm of Y my O2. It would be N log of the PO2 minus log of Kg. Okay, so N is what we call the Hill coefficient. And this Hill coefficient will measure the degree of cooperativity. Okay, so we can plot the Hill. So this is the Hill plot. For the myoglobin, the slope, so the slope will give you the Hill coefficient. For myoglobin, the Hill plot, it's equal to 1. It means that the bending of O2, it's not cooperative. This value is higher than 1. It indicates a positive cooperativity. This is the case of hemoglobin. The slope is around 3. What is a positive cooperativity? It means that the bending of one molecule of O2 facilitates the bending of an additional ligand, or the additional O2. Okay, so it means that when you one oxygen binds to one heme, the second oxygen with higher affinity to the heme. than the first one. Okay, so the bending of the first O2 facilitate the bending of the additional O2. And when you have an NH negative, lower than 1, it's called a negative operativity. So it means that the bending of one ligand the bending of the second ligand will be more difficult than the bending of the first ligand. Okay? We can see that the saturation curve of hemoglobin depends on several factors. The presence of CO2, the pH, okay? So for example, the pink curve, so it's at pH 7.4 without CO2, and the percentage of release of O2 will be around less than 70%. Okay? You know how to read this kind of curve?
No.
Okay. So you have to tell me. Okay. So the pressure of the lens, it's 100 torr. Okay? It means that in the saturation, yes, the saturation curve, it's 100%. Okay? So it means that in the lungs, hemoglobin or myoglobin are 100% saturated with O2. Okay? So this is this point. In the tissue, the pressure of the tissue is 20 torr. Okay? According to this saturation curve, we have the intercept between 20 torr and the saturation curve. So here, it will be here for the pink. Okay? It means that between the lungs where the hemoglobin is 100 saturated by O2 and the tissue where it's only, let's say, 35% saturated by O2, it means that when the hemoglobin will be transported from the lungs to the tissue, he will release, so 100 35%, it means that it would be 65%. Okay? So it means that in this case of the pink curve, at pH 7.4 and without CO2, when the hemoglobin will be transported from the lungs to the tissue, he will release 65%. Is it okay for you?
Yes.
So if I take this for the case of myoglobin, myoglobin in the lungs, it's 100% saturated with O2. But because of the hyperbolic curve, in the tissue, it's about it's about 80 saturate. Okay? So that's why the percentage of O2 release, it's not set 7%, but 18%, I think. So that's why the percentage of O2 released by the myoglobin is very low. Okay? So I told you that the oxidation curve, the saturation curve depends on the condition. So we saw that for the pink, you have 65% of O2 released, but when you decrease the pH of only 0.2 units, you increase this release of O2. It's 77%. And when you have a concentration of CO2, you need more oxygen, and then you have a release of 88% of O2. Okay? So what is the mechanism of the allosteric system? Okay? So I told you that the radius of the iron depends on the presence of O2. Okay? In the desoxy form, it means without O2, the iron is too big, too large, and then it will be below the heme, out of the plane of the heme. When it's coordinate with O2, so in the oxy form, the radius decrease, so the iron is fit to be into the porphyrin, so it's in the plane of the porphyrin. Okay. But the histidine, which is coordinate to the iron, it's attached to an helix. It is the helix H. Okay. So in the pink form, so pink form is oxy form, you have this position of the helix, and in the blue form, it means the desoxy hemoglobin, you have this position of the alpha helix. It means that you will have a twist. The alpha helix will change its position when you have the bending of O2 in the presence of O2 or in the absence of O2. And this will affect the other subunits. So in the desoxy form, you have hydrogen bond between the aspartate and the tyrosine. So the aspartate of the beta subunit and the tyrosine of the alpha subunit. So when you have the bending of O2, the F helix will change. And so all the subunits will change in the conformation, and you will have another interaction between the two subunits. In the oxy form, you will have hydrogen bond between this time asparagine and aspartate of the asparagine of beta 2 and aspartate of alpha 1. This is the same thing at the beginning, so in the desoxy form, okay, you have here the H bond between tyrosine of the alpha subunit and aspartate of the beta subunit. After that, after the O2 bend, you have a change in the conformation of the F, helix. So you will have now a H bond between the asparagine and the aspartate. Okay. So you have a small, you can see that it's like breathing of the proteins. You have the change in the conformation between the oxyform and the desoxyform. So we said that the hemoglobin is allosteric proteins. Okay. Maybe we can have a coffee break and we'll talk after about the another role of the metals, which is the oxidoreduction. Okay? So let's say 10 minutes of coffee break.
Yes.
Okay. Hello, I'm back. We will start with a quiz. Please connect you to the quiz. We're waiting for more player. No more player. So, should I start or 11 player?
Uh, please wait a bit more.
Okay. 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 We have only 12 players. Okay, I should start, and after maybe if other player can join us, it would be okay. Let's start. Yes, correct. I told you that arsenic is toxic, so it cannot have any function in the body. Question 2. Yes, correct. You need to bind a metal heteroatom. So valine, phenylalanine, and glycine, you have only H or carbon, hydrogen or carbon. So he cannot bind to metals. And aspartate has a carboxylate group, so he can bind easily a metal. Okay. Third question. Yes, you are right. Zinc can have only a 2 plus, oxidation state of 2, calcium it's also 2, and magnesium it's also 2, so copper can be 1 or 2. Okay. Oh, there's no oxygen on the histidine. It's only nitrogen. histidines, you know, it's a ring with 5 atoms, 2 nitrogen. Okay, so we probably have the winner between the two people who answer correctly. Yes. Okay, the last question. Sorry. So it's an easy question. Yes, it's iron. Nothing. Okay, let's see who is the winner. And who is Van Han? Show me your. You don't have camera? Ah, yes. Hello. Congratulations. Okay. I hope you enjoyed my quiz online. So, let's finish. We have a few slides and after an exercise of about hemoglobin, so maybe you will understand better about the saturation curve, and after this is the end of my lecture. Okay, so I have to share. I will stop my camera. Share. Yes. So, yes. Okay. So we saw with hemoglobin the role of some metals to bind some ligands. And now we will see the role of metal in electron transfer in the biological media. Okay, so electron transfer. So it will be oxidoreduction reaction between two species. So I'll give you some chemical clue. You should, I hope you know that already. So you will have this kind of half reaction. It means that an oxidant can capture some electron to be reduced, and a reductor can release some electron to be oxidized. And you have an oxidoreduction reaction. It's the reaction between two species, one oxidant and one reductant. Okay, for each half reaction, you have what we call the Nernst equation. Okay, so it's the potential of this reaction. It's involved, the temperature it's in Kelvin, the R is the gas constant. As usual, you have the Faraday constant, the number of electron transfer in the half equation. So this is this N. And in biology, we add the prime. This because it means it will be at pH 7. Okay. Usually you have this equation. Okay, this equation is when you are at 25 degrees Celsius. Okay, donc be careful. In this equation, you have the logarithm Neperian, and in this equation, it's more useful. Use is the logarithm, the log. Okay. So for an electron transfer, to be sure that you have a redox reaction, you should always, as always, when you have a reaction, you should have the free energy, the delta G should be negative. Otherwise, not be spontaneous. So you can have this equation. The delta G is related to the difference in the potential standard of the two couple, A and B, and to have a spontaneous reaction. So the ROX can react to the B red. You should have the delta E, the difference between the potential standard potential, should be positive. Okay. I don't know if you use this, we call that the gamma rules. If we plot the standard potential of each propel, we put on the left the oxidant, on the right the reductant, and the oxidant with a higher potential can react with the reductant with the lower potential. So, and it will give the oxidant 1 and red 2. Okay. So you have here a table with selected standard reduction potential of several. We will see that also several molecule which is involved in the electron transfer. So this is an example because maybe I don't have time for the exercise. So you transfer 2 electrons from NADH to oxygen. So the half reaction for the reduction of oxygen is the reaction A with a potential here. The reduction of NAD plus 2 NADH, so we will give 2 electrons. It's a reaction B. So it means that the whole oxidoreduction reaction is this one, and the difference between the potential are positive. So we can calculate the delta G, which is negative. So this reaction can occur. We can have also catalysis. So redox catalysis can happen when the standard potential of the catalyst is between the 2 standard potential of 2 couples involved in the slow reaction. So consider this reaction. You have 2 couples, A ox, A red, B red, and B ox. This reaction between A ox and B red is slow. You need a catalyst, and you choose a catalyst with the potential standard between the 2 potential standards of A and B. In this case, the reaction with AOX and red, the red form, reduced form of the catalyst, can occur, and it would be fast. And after the oxidation form of the catalyst can react with the reduced form of the B, and this reaction can occur because you have a difference which will be positive, and it's also faster. So these 2 reactions are faster than the slow one, the first one. Okay, so this is the same a way to describe the catalysis cycle. AOX will react with reduced form of catalyst, which form the catalyst OX. This form will react with the reduced form of B, and give the B OX. So some electron carrier in the body. You have the most common, the most known is NADH or NADPH. So it depends on the presence of phosphate on this link, and it will be oxidized in NAD plus or NADP plus. Okay. You have also FADH2 and FAD. So this is this whole molecule with the R here. And we have a reaction with 2 electron transfer. You have also coenzyme Q, which is known maybe if you use some moisturizing cream, in some cream with a face on your body, you will use coenzyme Q, because this coenzyme can react with oxygen species, and so it should reduce the oxidative stress. Okay. So you have coenzyme Q, which is also called ubiquitin, and you have also a reaction with 2 electron transfer to give ubiquinol. And you have, now you can recognize it, but you have an hydrophobic tail. So it means maybe this coenzyme is anchored into a membrane with a hydrophobic interaction. Okay, so you have organic species, can have electron transfer, NADH, FADH2, ubiquitin. We have also already seen the cysteine, because 2 cysteine with this style can make a disulfide bridge. So 2 cysteine can be reduced to form a disulfide bridge. Okay. And we also see in an exercise a very important redox compound in the body. It's the glutathione. The HH, you have to see the first part of the exercise. Okay, we have also redox proteins as electron carrier. So the redox center, it can be, as I said, the disulfide bridge. Okay, this is the equation I wrote before. You can have organic cofactor, which is called flavoprotein. So the organic cofactor will be with the coenzyme A of FADH or NADPH and so on. But you can have also a metalloprotein, so inorganic cofactor with several metals. Okay, and the advantage of having all this kind of redox center is to have a lot of potential value for the redox center environment. So you can have a redox potential from minus 700 millivolt to 600 millivolt. So for the FDA FMN prosthesis group, so this is this kind of structure. In this case, you have H bond interaction between FMN and the polypeptide chain, okay? Because you have this part which can give hydrogen bond. And you have also the R group can be a phosphate group, so he can make hydrogen bond with the proteins. You can have metalloproteins with the heme. Yeah, this is the same case with hemoglobin. This is hydrophobic part of the heme, so you should have an hydrophobic pocket, but you can have also electrostatic or H bond with 2 carboxylyl group. Okay. We have also another type of proteins which is called the blue copper proteins, which contain a copper, and the ligand will be the side chain of amino acid. So we already saw that, but you have serine, tyrosine with the OH group, the carboxylate group of aspartate and glutamate, the nitrogen, the thiol, and sulfur of cysteine and methionine groups respectively. Okay, and also I already tell you that you can have the oxygen and nitrogen of the peptide chain. So you can have the blue copper proteins with the copper and iron sulfur protein with iron. It's very simple. So an example is the cytochrome. I think it's cytochrome B. Okay. So it contains an iron in the center of your heme. So the oxidation state of iron can be between 2 and 3. Okay. And you have the structure. Okay. Have heme A. It means you have R2 on this side, on the A ring. You have farnesyl. It's a long hydrophobic tail. So with this hydrophobic tail, it allows the proteins to be in interaction with the membrane. It's always the same. If it's hydrophobic, the same interaction. It's about interaction, hydrophobic interaction, ionic interaction, or H bond. It coordinates with sulfur. The sulfur can form a bridge between 2 iron, and the other ligand of iron will be methionine or cysteine. You can have the iron sulfur with 2 iron, 2 sulfur, 3 iron, 4 sulfur, 4 iron, 4 sulfur. Okay. And you have this kind of equation. So it means that the iron will be between the oxidation state of 2 or 3. And you have a crystalloid structure in the human ferredoxin 1. So this is 2 iron, 2 sulfur, and the iron is linked tightly bound to the proteins with cysteine 1, 2, 3, 4 here. Okay. Yes. For the blue copper, why we call blue? Because the copper, you have a coordination between the copper and several amino acids. side chain. So the oxygen of the glycine is not a side chain, it's a peptide chain. The nitrogen of histidine and the thiol group of the CTR. And it's called blue because the solution is blue. It's very simple because of the copper, of the presence of the copper. If you remove the copper, you have a white solution. So we have a lot of examples of blue copper, delacyanine, azurine, plastocyanine, rusticianine, and each of these protein has different potential, standard potential, okay, depending on the coordination of the copper, okay, the coordination and the length of the no, it's the same. Ah, no, it's the plastocyanine. Sorry, this is not rusticianine. I put the same. Okay, so the potential depends on the nature of the ligands of the copper and also the length between the ligands and the copper and the geometry of the copper. Okay, so that's why I told you it's very important to have several proteins because you can have a lot of proteins with a large range of potential. How to measure a potential standard? I give you two techniques. The first one, it's called, it's not written. In the first one, you will combine two techniques, electrochemistry and spectroscopy. So in here you have electrochemistry. And spectroscopy. You have, sorry. Sorry. You have a cuvette with two electrodes and you can measure in the same time the potential of the protein between the two electrodes and the absorption spectra of the proteins. So you will can obtain then, you can plot then the potential, the ratio between the oxidized form and the redox form, again the potential, okay, because the oxidized form has a different spectra than the reduced form. So you can plot this kind of curve and you can obtain from the slope from the nearest equation. This is the slope of this. Okay, the slope of this curve will give you the number of electron transfer for this between the oxidized and reduced form. And from the intercept of this curve, you will obtain, sorry. The intercept will be here. From the intercept of this curve, you will obtain the standard potential of the redox copper. Okay? So this is the way the number of electron transfer and the standard potential of a protein, for example. You can combine electrochemistry and spectroscopy. You have another techniques which is called cyclic voltammetry. I cannot explain very currently, but you measure the current between three electrodes and again the potential. You will have this kind of a curve. I call that a duck curve. And we measure the potential, the redox potential, and the reduced potential and the oxidized potential, and then you can obtain the standard potential. Okay, and I never use this, so I cannot very explain to you these techniques. Okay, you have in this table a lot of potential standard are pH 7. That's why you have the prime of some redox system involved in biological electron transfer. So you have redoxin, NADA, NADPH, FADA, FADH2, and so on. When it's free and when it's bound to proteins, the potential will change in the presence of proteins. For example, you have cytochrome C, cytochrome C1, which is in proteins with iron. Okay, the risky protein is with iron sulfur cluster. The cytochrome is usually with heme. Okay. So, you know the glucose metabolism. It occurs in the mitochondrium. So you have the mitochondrium here with an intermembrane space, the matrix, outer membrane, inner membrane. Okay, you know that glucose will we have the glycolysis of the glucose and give some electron because it's a reduction. Okay, this give you pyruvate. So these two kind of molecules, pyruvate and fatty acid, come from foods. Okay, and these two molecules, pyruvate and fatty acid, will be transformed onto acetyl coenzyme A. This acetyl coenzyme A will be submitted to the citric acid cycle, and in the citric acid cycle you will form CO2. Okay, so this is the respiration from O2 to CO2. Okay, and what happened from O2 really easily? From O2, you know, O2 it's neutral, so it can easily be transported. It can easily cross the membrane, and O2 will be reduced to H water, and because of electrons transport change in the mitochondria, you will have this electron will give you proton, and with ATP synthase you will make a form from ADP, ATP. Okay, so you will have a lot of ATP. So the respiration from O2 to CO2, it's involved a lot of proteins, which is called electron transfer change. These proteins are usually cytochrome. Okay, so it's very important to have proteins we can have redox potential. That's all for today, and we have to finish an exercise about hemoglobin. I give you 5 minutes to read this, and after I will give you the question. So I can read with you. So the blah blah, it's hemoglobin, okay? Just you have the structure. So we will, in this exercise, we will plot the saturation curve of hemoglobin in the presence of this molecule, okay? So to do that, we will record the absorption spectra of hemoglobin in the presence or in the absence, of oxygen, okay? So the figure below shows the titration of a solution of hemoglobin by oxygen, okay? The protein concentration is 75 micromolar, and the percentage given is the proportion of oxygenate hemoglobin. So what is the wavelength which reflects the conformation change induced by the oxidation hemoglobin? So we take where the difference in absorptions is the higher. So we will take this wavelength, which is approximately 575 nanometer, or here, which is 560 nanometer. We can take these two wavelengths, for example. Okay, so calculate the molecular extinction coefficient. Sorry. The molar extinction coefficient of the hemoglobin, oxyhemoglobin, and desoxyhemoglobin at this wavelength, so 560 nanometer, given that the optical length it's 1 centimeter. Okay, so which law we will use to do that? Which law can give us the molecular absorption spectra coefficient? We will use the Beer-Lambert law. Okay? So what is the equation of the Beer-Lambert law?
Is A is equal epsilon multiplied by L multiplied by C.
Yes, absorption, it's proportional to the concentration. So this is the concentration. You have the length of the cuvette and also the epsilon, which is the molar absorption coefficient. Okay? So, for example, the epsilon of desoxy. So the epsilon of the deoxy, I will take the absorption here, okay, without oxygen. And because I know the concentration, which is 75 micromolar, I can calculate this epsilon. I give you the answer. The epsilon of the oxy, it's about 16,700, and the units, it will be mole -1, liter, centimeter -1. I can do the same with the oxy form. Okay, the oxy form, I will take this plot, so it's the absorption, it's around 1. Okay, so I will make 1 over, the length is 1 over 75, 10 minus 6. So I have epsilon around 13,300 molar -1, lit, centimeter -1. Okay for that? Okay. So now we study the mechanism of oxygen bending by UV visible spectra in the presence or in the absence of BPG. Okay? For each value of oxygen pressure, it records the value of the difference in the absorption at 560 nanometer between the hemoglobin solution with oxygen and a reference solution of hemoglobin. For all experiments, the total concentration of hemoglobin in each curve is 610-5 molar. Okay, so I will explain. Sorry. Let's, I would add another. So if you I will give you the slide so you can read it again, but in the experience, in my experiment, you have 2 cuvettes. One is the sample and is what we call the reference. At the beginning of the experiment, you have desoxyhemoglobin in each cuvette. And you will add oxygen only in the sample one. Okay? And the concentration in the 2 cuvettes, it's 610-5 molar. Okay? We can say that the total concentration of hemoglobin, which is 610-5 molar, will be at each time the desoxy form and the oxy form. Okay, because all the desoxy form of hemoglobin can react with O2 to give the oxy form of hemoglobin. Okay? Tell me if you don't understand. I try to go slowly, but okay. The absorption we measure. So the difference in absorption will be the absorption in the sample minus the absorption in the reference. Okay? So absorption in the sample, it will be the absorption of the desoxy, the absorption of the oxyform minus the absorption of hemoglobin at the beginning of the experiment. Okay, so the delta A, I will use the Berlin law. It will be epsilon desoxy L desoxy. I use Berlin law for the absorption of the oxy form of hemoglobin minus at the beginning all the hemoglobin are in the desoxy form because there's no oxygen. Okay? You still there? Okay, let's say you still there. So, the desoxy concentration of the desoxy, I can use this equation, right? So I will be desoxy L, it will be HB0 minus oxy. I will don't change the rest of this equation. Okay? So at the end, I will have epsilon oxy minus epsilon oxy L so you will remove this. You have only the oxy form. Okay, so the absorption we measure, it's proportional to the oxy form. Okay, so we can from the experiment obtain the oxy form, which will be minus different delta A, epsilon, sorry, I changed. It would be desoxy minus epsilon of oxy. Okay, and the Y, we have to define the Y. The Y is the saturation, okay, is the fraction of oxy over the total concentration of hemoglobin. This is the definition of the Y, saturation fraction of protein which binds to the oxygen. Okay? So, because we have the concentration of oxy, because we have the difference in absorption, we can plot this, right? Right? So let's see. I will add a new slide. And so I plot for you. So from this experiment and this equation, I plot the y for the two experiments, experiment 1 and experiment 2. Okay? You still see my slide? Yes?
Yes.
It's okay now?
Yes.
Yes? Okay. So it's in the presence of two, 3 D, P, G. Okay, so here you have the Y, the fraction of hemoglobin, which is in the oxyform, and here you have the pressure of oxygen in millimole of mercury. Okay, so they said that the pressure in the lungs it's 50 millimeter of hemoglobin, so it's here. So you have the lung here, okay, and the one of the muscle it's 5, okay, so it's here. So we have to determine from these two experiments the percentage of oxygen that is released when hemoglobin reach the muscle. So when hemoglobin are in the lung, the saturate value is 40%. Okay, and in the presence of 2,3 BPC at a pressure of 5 millimeter of mercury, this is here. Okay, so the Y it's only 20%. It means that the release it's 78% of O2 released in the presence of this molecule. In the absence of the molecule, in the lungs, you have also a Y at 98%. Okay, at 5, I will change the color. That at 5 millimeter of mercury, this time in the absence of the molecule, the Y curve will cut here, around here, at 5 millimeter of mercury. So you will have this point, it's about so 76%. So sorry, I'm wrong with my, it's 96%. So release it's only 76%. And here you have only released, so 20% of oxygen released. Understood or not? how to read this kind of curve. You take the point of the pressure in the lungs. So this point is correspond to 90%. At the pressure in the muscle. So for the blue one, it corresponds to 20%, and the light blue, it corresponds to 76%. And you make the difference between these 2 points, and you have the percentage released of oxygen. So in the presence of BPG, you can release 76%, and in its absence, we release only 20%. So it's very few. Okay, so the physiological roles of BPG is to allow a higher release of oxygen. Understood or not?
Yes, I understand.
Okay, and the other?
I understand.
Okay, yes. Okay, so if you don't have any question, we can stop here. If you have any question, I can stay. So I don't know when will be the exam, but if you have any question, don't hesitate to write to me just before the exam. Okay, if you have questions. So do you have question?
Yes.
Yes.
There was some part that I didn't really catch up. I didn't follow. I couldn't follow the part about the oxygen saturation.
The equation?
Yes, most of the equations confuse me.
Oh, you don't have I can explain again if you want, but it's mathematic. Oh no. Sorry. No, I have to share first. Oh. Let's share. This part, right?
One before that.
This one.
Yes. I think the two slides you just showed, they are related, and I didn't really understand from this part.
Oh, to measure the efficiency of an enzyme, you measure its enzymatic activity, but hemoglobin is not an enzyme. So to measure the efficiency of the hemoglobin or myoglobin, you measure the saturation curve of the proteins against the pressure of oxygen, because the oxygen is a ligand. So the definition of the saturation, this is it. This is it. So it means this is the fraction of proteins who binds oxygen, its ligand. So at the beginning, so this is the oxyform, the fraction between the oxyform and the total concentration of myoglobin, even if it's in desoxy or oxyform. Okay, it's a definition. So if you have this equation, you can define a thermodynamic constant, which is the affinity constant, or in biology we prefer the dissociation constant. Okay? In the dissociation constant, you should have it is the ratio between the activity of each molecules. For solution, you have the concentration, but for gas, you use the pressure. This is it. So you need, for example, sorry, you can from this, I can have the concentration of the oxyform. It will be NPO2 over Kg. Okay? So I will put this expression in this. Okay? So it will be give you YO2 MB PO2 over Kg. Okay? And MB, it's too low. Sorry. I would put here. So I put this equation of the oxyform of hemoglobin in here. Okay? So it will be MB PO2 over Kd MB plus MB PO2 over Kd. I can divide by MB. So it will be PO2 over, it would be 1, PO2 and Kd. So we find this equation. I don't know if I answer your question.
Yes, it's more.
This is, tell me.
Yes, it's better.
It's
I
better?
understand.
Okay. Okay. Is there any other question? No question? Maybe after you see it again, all the slides, you may have questions, so don't hesitate to write to me. Okay?
Okay.
Okay. That's all. I hope you enjoyed the lecture, the quiz. It's very difficult to me to make lecture by Zoom, but maybe next year I can go to Vietnam. I hope. Okay, so bye. I don't know if you have Christmas holidays, but Happy New Year and so on and so on. Merry Christmas and bye.